Suppose I'm given a function f of x, and I want to know what is the average value of that function on an interval from a to b. Well, I'm not sure quite how to begin, but I do want to leverage some of the ideas that we used in computing area under the curve, volumes, and arc length. So maybe my notion of average value of the function is the average of points that represent the function. So maybe I can take a bunch of points that are equally spaced along the function, and I can label them. Maybe I'll label them f of a. Maybe this one will be f of x1, f of x2. So this is x1, x2. This one would be f of x3. And then I could continue along to f of xn minus 1 and f of xn, or f of b if you like. And maybe I could find the average of those values that represent the function. Because I understand how to find the average of a list of numbers, so maybe that'll represent the average of the continuous function. Now, of course, the more points I use, probably the more accurate my estimate is going to be. But it's still just going to be an estimate because I'm trying to represent an infinite number of points here and find the average. Well, let's follow that intuition. So we're going to find the average value of a bunch of points. We'll call them f of x1 through f of xn. So to find an average, just thinking about how we found averages in the past, you're going to add up all the values all the way to f of xn, and then just simply divide by n. We could write this as the sum from k equals 1 to n of f of xk times 1 over n. And here, I'm going to think about these points as being regularly spaced. So I'm going to think about x sub k as being a plus k delta x, and then delta x would be the length of my interval, b minus a over n, so that each of these points is regularly spaced. Well, okay, I'm going to take my formula for the average here. So this is the sum from k equals 1 to n of f of xk times 1 over n. And I'm going to multiply the top of this by b minus a, and I'm going to multiply the bottom by b minus a. So I haven't changed the average at all. But I now have 1 over b minus a, sum from k equals 1 to n of f of xk times delta x, because b minus a over n is delta x. And now this looks like a Riemann sum. Well, we've talked about already that if we used more points, we could increase n in that way, increase the number of intervals that I'm looking at, the number of points I'm using to represent the function. And that would make our estimate more accurate. Well, what if we took the limit as n goes to infinity of our formula for average value, which is 1 over b minus a, the sum from k equals 1 to n of f of xk delta x. Well, that would be an integral. That would be 1 over b minus a times the integral from a to b of f of x dx, because the Riemann sum converges to an integral. And that is going to be our formula for average value of a function. So if we have a continuous function from a to b, that's just so that the integral exists, then the average value of that function is going to be 1 over b minus a times the integral from a to b of f of x dx. And we call that average f bar because often we call a mean or an average value of a quantity that letter with a bar on top.